Hi Anant. Hi Ravika.
Hi Nilesh. Maybe we can wait for one more minute and then we start. Oh, I was on mute. So hi Nilesh. We'll start maybe in 1 minute, or I guess we can start now. It's already. Let's. Yeah, I hope I'm audible, right?
Yes, you are.
Sure. Okay. Yeah. So welcome to the live session for the week 4 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be taking the assignment problems which are similar to the assignment that have been given to you for the week 4. So let's go towards the course content. So till now we have already covered like the very basic of the devices. We have covered mainly the physics part, like how electron moves inside a device, not a device but for a material, let's say for a silicon, how, what is the mobility, why does it saturate, what is this Fermi Dirac function, etc., and like why it is probabilistic, not actual, like there is no certainty, that is what we call as Heisenberg uncertainty principle. And at the last we covered the concentration, that is what is a doping, or what is the concentration required to have more amount of current or something like that. So like keeping this in mind, today we'll be starting with the first device that has been signed in the course, that is a p-n junction diode, which is like the most basic device for some operations that can be used. So I mean, you might have heard like in a very layman language that diodes are what they call are like something like the unipolar devices, which only allows the current in one direction and it blocks the current in the opposite direction. So that is what p-n junction is. P-n junction is nothing but a diode only. So we'll be starting with the equilibrium condition, in which we'll not be applying any bias, and then we'll see some of what is the IV relation. I guess I'll not derive it, but yeah, I'll give you the idea that why does it look like the IV relation look like that for the p-n junction diode. And then there are like few concepts, some such as non-idealities of p-n junction, etc. So I guess for the week 4 and 5 I'll be covering, like I'll be taking, there might be some topics of week 5 in this lecture, or there might be some topic of week 4 in the next lecture, because the very basic understanding of band bending is required. So I'll be starting with the very basic junctions. I'll be letting you know how the band bends, or how do you make a band diagram for a any device, not, let's say, not even p-n junction, but let's say for a npn, which is a bjt, and even for a MOSFET. So once you get the concept of the band bending clear, then yeah, maybe you can make bands for any devices. So we can do some exercise on that also. So yeah, like this was a very basic introduction. So let me start, as I said, with the topic of junctions only. So I mean, we'll be first looking into the band bending, like how do we make bands for or a band diagram for any device. So we'll be doing the p-n junction in this particular lecture. So we'll be seeing how do we make a band diagram for a p-n junction. Some of you might already be knowing it, but I'll go through it very quickly so that you will have a better idea or a better understanding for the same. So okay, so can anyone tell what does the band diagram shows? I mean, why is it helpful? Anything will work. I mean, any basic idea? What is the use of band diagram?
Where is the Fermi energy?
Okay, yeah, so there is Fermi. What else?
A flow of electron, like from which material to which material it will flow.
Yeah, that is good. So basically, first of all, as we have already like established that this band diagram are energy band diagrams, and we know that energy is nothing but, if we write in a very basic terms, it is nothing but charge into potential, right? So band diagrams are also a measure of potential, and once we know the potential, we know the electric field, right? Electric field is nothing but the gradient of the potential, maybe minus dV by dx. So band diagrams can help you analyze anything, such as the potential profile, which is this V, such as the electric field profile, which is this E, etc. So once you have a band diagram for any device, from the band diagram itself you can tell what is happening, or what is the type of device, or what are the different types of concentrations, and that you can also tell using the Fermi level that is being presented in the band diagram. So first of all, let's say that we are at a thermal equilibrium, even we are not applying any voltage, and we are at a equilibrium. For this condition, what will happen, or what happens is, whenever we join two materials, let's say two materials, we have two materials, and when they are joined at thermal equilibrium, what happens, their Fermi level align. We'll be seeing how they align, and maybe quickly using some very basic mathematics. Yeah, so let's say as I said, let's say I have two materials, one is material 1 and one is material 2, and let's say the material 1 has a density of state G1 and material 2 has a density of state G2, and similarly it has the Fermi Dirac as F1 and F2, the Fermi functions, that is Fe, that we studied in the last lecture. So I'm assuming you already have the idea that this is what is concentration. I mean the density of states times Fermi Dirac, the integration of that is concentration. So I'm assuming that you already have the idea from the theoretical lecture that you might have covered now. So I mean, let's say we have two materials. So let's say this F1. So what will be F1? Can anyone tell quickly? 1 upon? Um,
1 plus e to the power of minus
yeah. So something
divided
like
by
that. E minus EF1. So I am denoting the Fermi level for the first material as EF1 by KT. And similarly, we have F2, which will be the same, and it has its own Fermi level, let's say E minus EF2 by KT. So this is what we already know. And as I said, that electron concentration, let's say N1 is for the first material, it is nothing but F1G1, and the second material, it is nothing but F2G2. The density of states times the Fermi probability gives the electron concentration. Similarly, the whole concentration will be, can anyone tell what will be the whole concentration in terms of F1 and G1 only? Okay, so let me give a very basic idea.
1
So
minus f1.
yeah, that is nice. Okay. So I see you have some understanding. So 1 minus F1 times G1 will be the whole concentration, because the whole probability needs to be 1. So 1 minus F1 gives you the probability of holes at that particular energy level. So similarly, it will be 1 minus F2 times G2. So now what we know is, like from basic physics, that at thermal equilibrium, what we know, that the flux is constant. I mean the flow of material, or the flux from left to right in a material, is constant. So what we write in general is, so flux is nothing but the concentration multiplied by the holes. So I mean the electron concentration multiplied by the hole concentration in the opposite end. So because from one of the solids, let's say N1 is traveling from left to right, so for that particular solid, this P2 will be coming from right to left. So that is why I have written N1 P2, and this will be equals to N2 P1. So the flow of charge, or the flow of carriers, are constant at thermal equilibrium. So I just need to put the basic values. So N1 we just established, it is nothing but F1 G1. P2 is nothing but 1 minus F2 G1. Please let me know if I have written something wrong. I guess it is correct. Yeah, N2 is F2 G2, and P1 is 1 minus F1 G1. So if you try to open it, what I'll get is, first of all, G1, sorry, this will be G2, right? So first of all, G1, G2 will get cancelled out. What I've left with is F1 minus F1 F2, and this is F2 minus F1 F2. So I can cancel it. So what you see is the Fermi level, or the Fermi functions, are same, first of all, okay, not the Fermi level. So if we have the same Fermi level, and as you already know, 1 upon, this is 1 upon 1 plus exponential E minus EF1 over KT, and this is what is getting equal to 1 upon 1 plus exponential E minus EF2 over KT. So what do you imply from this? If F1 is equals to F2, so what will be equal in these two things?
EF1 is equal
Yeah.
to EF2.
So that is what I was trying to say, that the Fermi level aligns at thermal equilibrium. I mean, there will be a single Fermi level even if you have two different materials at thermal equilibrium. So yeah, that is a key takeaway. So maybe I hope you are already aware of some of the terms that might come further. So let me give a very basic idea. So can anyone tell what is work function? There are two terms. One is work function and one is electron affinity. So work function looks something like phi. This is yes.
Energy required for an electron to move is a work function.
Energy
Electron
required
accelerator,
to sorry, energy required to move from what?
for an electron to move,
From where to where?
valency band to conduction band.
Okay, that is band gap, no? That is the
Yeah.
forbidden energy band gap.
It is to remove the electron
Yes,
from the surface
from the surface to.
to the, outside.
Okay, so let me give you a very basic idea again. So what we have is okay. So what we have is we have the band diagram EC EV, which you already know. Let's say this is, let's say, vacuum, and for instance, let's say this is the Fermi level somewhere. So let me mark what is what, then you will get the idea. So from this to this is, and this to this is already in electron volt, yeah. So let me repeat, I guess you're not clear about that. So the energy required to remove an electron from Fermi level to the vacuum level, from Fermi to the vacuum, is nothing but work function. And the energy required to remove an electron from conduction band to vacuum is nothing but the electron affinity. Make sense? Any doubt in this?
Yeah.
Yeah, so this is the more clear definition. So what happens is this work function for metal and electron affinity, it will be for, let's say, silicon. Okay, sorry, what happened? Hmm. For silicon, they are material properties, so they will not get affected by the different device design. Sorry again. My screen went away, right?
Yes, we are not able to see.
Okay, give me a moment. Can you see now?
Yes.
Okay, yeah. Hmm. So what I was saying is that these are all material properties. So very basic example, if I try to show, I mean, this is analogy taken from a water reservoir. I mean, all of the faculties teach like this only. So let's say we have a single reservoir which is having a Fermi level EF, and once, let's say, we join two, let's say this is what it was filled before and this is what it was filled before. Let's say this is EF2, and once we like open them, so what happens is, let's say this is our water bucket. So what do you think will happen? How the water will move from, let's say this is bucket 1 and this is bucket 2.
From one
From
to two.
Yes. So if you treat water like an electron, so what happens is, so let's say this is Fermi to vacuum. So this will be, let's say, phi 1. This is Fermi to vacuum. So this will be phi 2. So you see here phi 2 is greater than phi 1, right? So when two semiconductors are joined, so what happens is there will be some flow of electron, like you said, from 1 to 2, and the Fermi levels get aligned. So after this, there will be a single something like this, a level at which they will become equal. So I'm clearly talking about thermal equilibrium right now, or the equilibrium condition. So please keep in mind that. So I mean, to summarize this, when two semiconductors are joined, then the electron will flow from the material having a higher Fermi level to the material which is having a lower Fermi level. And that is the electron flow from the material having lower work function, that is phi 1, to the material having a higher work function. So please keep in mind this. And now if I try to make a band diagram out of it, I mean, let's say we take some example. So this is ECEV, and let's say this is EI. Let's say I'm taking a, not right now, EC, this is EV, and this is EI. So let's say this is EF and this is EF. So first of all, quickly let me know what is material 1, the type of material, and this is let's say 1 and this is let's say 2. So quickly let me know what is material 1, I mean which type.
P-type,
Yeah, and 2 is.
P,
N-type.
So how the flow of electron will be if we try to join them?
Um,
from
in
N to P.
2P, yeah.
Yes, from higher Fermi level to lower Fermi level, or from a lower work function, let's say I'm denoting it as phi n, to a higher work function. So if I try to, yeah, so this is how the flow of electron will be. This is what I wanted to let you know. And you need to just focus on how the electron move and how the conduction band edge will move with respect to the Fermi level. So this is the conduction band edge. So to move this electron from here to here, so this whole thing will somehow come down. I'll let you know the exact band diagram. I mean, this is just a basic idea. So this is what we call as band bending. So there will be some bending of the, bending means BENDING, not BAN. So there will be some bending of the bands, and that is how we make the band diagrams. Now a thing to notice is that the interesting things or the any phenomena that is happening physically is happening only near the junctions. So this is the junction of two material. Nothing interesting is happening here. So we are not interested towards the bulk part, but we are only interested towards the junction part. So we'll be like solving most of this equations at the junction only. So now to have this, we have Gauss law to solve the field profile. So can anyone tell which equation is used to solve the electric field or the potential? I mean, those who have maybe have gone through some TCAD or something like that might be aware of this. Any guess? Also,
Can you repeat the question?
I'm asking that which equation or which universal equation is there to solve the potential profile or to solve the electric field profile. Okay, I hope
And
you
you
should
did
have heard it.
mention because
Have you heard about the Poisson's equation? Everyone? Yeah.
yes,
So what is Poisson equation? Any idea? I mean, any guess? Okay, I think not. So it is nothing
some
but,
Laplace equations and all come in picture.
yeah. So Poisson equation basically gives you the electric field behavior, or you can say it also gives you the, if phi is the potential profile. So this is the key equation which is getting solved in each and every, let's say, simulation software that you might be learning in this course. I'm not sure. TCAD is one of that software. So TCAD does it solves this equation at each and every point, and it determines the potential at that point. So this is how you will get the band diagram. So band diagram, as I said, it is nothing but a potential profile representation. So this is what we will be using to do the derivation or to have some more clarity about the PN junctions also. So let's quickly make the band diagram for PN junction now. Can I make it here? No. Let me quickly make it. So this was EF for P, and so let's say I'm writing it as EFN and this is EFP. Sorry. So this is what we have already established, that the electron movement will be from higher Fermi level to a lower Fermi level. So what is happening is this whole part is getting, hmm, So what is happening is this whole part is basically getting shifting downwards. So let me try to make it to give you the idea. So again, I'm talking about equilibrium. So first of all, what do you think? What will happen to the Fermi level? If let's say if I join,
They'll align.
Well,
yes, exactly.
yeah.
So let me make that line first. So they will align, right? So let's say this is the Fermi level that has changed now. So what will happen is this thing is going, so the electron is flowing from P to N. So let me try to make, sorry, this is bad. Oops. So this is EC, this is EV, this is EF. So since the Fermi level is aligned, so what will happen? This conduction band will also shift accordingly. Since this is an anti-material, right? So for that there will be some band bending. So this is EF1 as I have already written. So similarly this EIE line will also be there, which is EG by 2. And what is happening is there is a gradient coming at the junction. Okay, can anyone tell what does this signify this gradient?
Concentration gradient.
Yeah, something like that. Okay. So as I said that this is nothing but energy band, right? Energy band is equivalent to the potential profile. So a gradient in potential profile means there is a certain electric field associated, right? So we have some electric field associated at the junctions, while since this is a constant, so the gradient will be zero. So there is no electric field associated in the bulk part. So that is why I said that we'll only be focusing on the junction part. So I mean, is it clear that how this diagram has been made? So this is P, this is N, and this is the junction. Is there any doubt in this band diagram?
No.
Okay, so maybe if not, then maybe I have a question. Yeah. So can you quickly tell which is the correct band diagram for this? So this is N plus, this is N, and this is P.
First one,
Okay, why? Why?
N plus has a larger concentration and N
Yes,
has a, so the Fermi level will be at the near to the CEC,
yes,
and then N is a lesser concentration than N plus.
yes,
It has little bit lesser than that, and P has a lower concentration, so it's near CEV.
exactly. So, everyone, are you able to understand what she just said? Any doubts in this?
Yeah, understood. I mean, the
Yeah,
work function is changing.
yeah. So similarly, how like the work function is changing, so the EC profile is also changing, the conduction band profile. So option A will be the correct answer to this. I mean, this is just for the understanding, but yeah, it's good that you can think that how these bands are bending now. That was the sole intention of showing all this. Yeah. So if we are clear now, so let's go towards the PN junction. Think more of the physics side of that. So PN junction is nothing but a single silicon bar, let's say, which is getting doped with different types of impurity at one end. Let's say P at the one side and N at the second side. So there is no two bars which are getting joined here. So please try to understand that there is a single silicon bar which is getting doped uh, using the whole concentration on the left side, and which is getting doped with a electron concentration on the n side. So I'm not applying any, let's say, what to say, I'm not applying any bias currently, so we'll understand what will happen or how does it work. So in the P type, what will be the majority carriers?
Holes.
Yeah, exactly. So the minority carriers will be the electrons or the acceptor ions. So these are acceptor ions, and let's say I'm denoting Let's say I'm denoting holes with the blank circles, I mean the hollow circles. And similarly for n type, the minority carriers will be this donor ions and the majority carriers will be the holes. So I'm like filling them now. Even if I not apply any bias, what do you think will happen once we try to join these two things?
Electron and holes start to recombine near the junction.
Exactly. So this electron will try to move towards this p type because it will get attracted towards the holes, and these holes will try to move towards this right side because they will get attracted towards the electrons. And there is possibility, as she said, that there can be some recombination. So these two can get recombined and make a neutral region for that. So let's say we are not thinking about recombination, but the first thing that comes to our mind is that this electron will move from right to left and this holes will move from left to right. Makes sense, right? So this P will have some acceptor ion concentration Nd, oh sorry Na, and this N will have some donor ion concentration which is Nd. So what you see if I try to plot, sorry, what is happening? Hmm. Yes. So if I try to plot the electron concentration versus the hole concentration, let's say, so what you see is, let's say this is some concentration Na, and let's say this is some concentration Nd. So what you see, there is a abrupt change in the concentration at the junction. So this junction is called as metallurgical junction. So here you see there is a abrupt change in the concentration. This is what I want to say. And as I said, the hole will be moving from here to here. So let's say hole diffusion. So this is called as diffusion. The movement from higher concentration to lower concentration is what we call as diffusion. And the electron diffusion will take place from here to here. So this figure, it is important to note that the entire semiconductor, first of all, is a single crystal. There are no two crystals. One side is doped with a highly p-type or acceptor ion concentration, and one side is doped with a n-type of concentration. And for simplicity, what we have considered is we have considered a step junction. That is, the concentration profile is constant for the whole p bar, and the concentration profile for the donor concentration profile for n type is constant for the whole bar. I mean for the x-axis if I say, so it is constant. So again, as I said, so what happens, the majority carriers electrons in n region will begin diffusing into the p side, and the majority carriers holes in p region will begin diffusing in the n region. And as I said, if we assume that there is no external bias, so do you think it will happen infinitely? uh,
I have one question.
sure, sure.
What is this? Graph which is indicating Na and Nd. I mean, with respect to position.
I lost your voice. Hello, am I audible, everyone? Please confirm. Uh,
Hello.
yeah, am I audible?
Hey, you're audible now. Did you understand my question?
I did not hear it completely. Can you repeat?
Okay, okay. So you have drawn this like the metallurgical junction. So Na and Nd. So what is this graph representing? I mean, one is the carrier concentration. Hello.
Yes.
I mean, I didn't get that.
So
Um,
give me a moment.
X is the length of the material, like
Yeah,
P and N.
yeah. So
Okay.
what I'm trying to represent here. So with respect to position, we will have some Na doping, right, in this material. So it is constant for the p type Na, and it is constant. Let's say some value of Nd for the n type, right? So what I'm
Uh-huh.
trying to represent here is there is a concentration gradient in the between. So this will be, let's say, 10 raised power 16 per centimeter cube of acceptor ions, and let's say this is, for example, this is 10 raised power 14 per centimeter cube of uh, donor ions. So there is some concentration gradient. So this is what we call a step or
Okay,
abrupt
okay.
junction. You see in most of the p-n junction problems, they write abrupt p-n junction. So this is what is abrupt, like a step. Make sense?
Okay. Yep.
Yeah. So what was my question? I was asking that, so do you think that this diffusion will take place infinitely? I mean, it will never stop.
No, uh,
Yeah,
it will be finite.
yeah. So it will be finite. So at once this electron diffuse from p side to n side, sorry, from n side to p side, and once the holes diffuse from p side to n side, what happens is, hmm, there are only what we are left with at the junction is, let's say there is some recombination, and so what happens is, let me make it again, it will be some confusion. So this is p side, right? So once this, again, so once this diffusion ends, what happens is we are left with the acceptor ions on the p side and the donor ions on the n side. So do you so now you see this region is depleted of mobile carriers, right? Depleted of carriers. Any doubt in this? Please let me know if there is any doubt.
No.
Yeah. So since this is depleted of carriers, so that is why we call this region as depletion region also. So I hope this is clear. I mean, this is the very basic. So the net positive and the negative charges in the N and P region induce this uh, electric field now, which is from higher potential to lower potential. That is what we discussed in the previous class. So that is why at the junction, I just made this band diagram. So that is why at the junction you see this band bending. So this gradient in like tells that there is some electric field, and it is always up the hill. Up the hill means the band, whatever the band is going up, the electric field direction will be in that direction, up the hill. From the band diagram also you can tell the direction of electric field. That is what I want to say basically. And this region is also called as space charge region, depletion region. I mean, there are various names of it, but yeah, this is a very basic of this PN junction. So if I try to, in we have established everything, I guess. So if I try to again, like in a very basic language now, so we have already seen. So let me make the complete diagram only. So this is EFN, this is EFP, which is aligned. This is EC, this is EV, and this is EI, this is EIP, this is EIN, ECN, EPN. Yeah, so I hope, I mean, this is all clear. So what we said that, let's say this is some, the difference between this EFP minus EIP, let's say this is some P side potential, which is Q phi P. And the difference between the Fermi to intrinsic, this is Q phi N. So can anyone first of all let me know what is the formula to calculate this difference between the Fermi and the intrinsic? So does anyone remember it from the previous class? Let's say this is P time material, and if I want to calculate EF minus EI, what will I do? Anyone? Come on, we did a lot of problems in the previous class. Okay, am I audible?
Yes, yes, you're audible.
Do you remember this formula?
This we know, yeah.
EI minus EF over KT. So this EI minus EF is nothing but Q phi P, right? So this is what I wanted to just elaborate. So basically the difference in the potential or the EI level is nothing but what we call as the built-in potential, which is what we denote by VBI. This is a very, like a very go-to term. So in general, there are a lot of diode problems in which they will let you calculate this built-in potential only. So first of all, again in thermal equilibrium with zero applied bias, no current exists and no external excitation is applied. So in this case, Fermi level is constant. As I said, this EFP and EFN are a single line. And what will happen now in the band diagram? Electron will easily move down the hill. That is from the lower potential to the higher potential. Similarly, holes will easily move upward the hill. That is from higher potential to the lower potential. And the electrons in the conduction band, let's say the electrons in the conduction band of the n side see a potential barrier. So you see this is the barrier. This is what they are seeing. This is the barrier, right? So from EC to here, so this is the barrier they are seeing. So this is the exact same difference that I have made here, because the same bending is happening everywhere. The EI is also bending like that. So from here, can we write that Q VBI is nothing but Q phi P plus Q phi N? Any doubt? Please let me know if you have any doubts.
No.
Yeah, okay, great. So I can write that VBI is nothing but phi P plus phi N. So let's do the derivation quickly. I mean, this is very easy. So let me do it. Okay. So as I said, phi p can be calculated by the same formula that I just said. So it is p. So p will be Na equals to Ni exponential of Ei minus Ef over Kt. So EIP, let's say, or minus EFP over Kt. And similarly, phi n will be, can anyone quickly tell now? So this is phi p.
Ni exponential EIN minus EFN by KT.
Okay, EI will come first for the n type. Think a bit.
Then EFN
Yes, that is,
minus EFN
yeah.
minus
So
EIN
this
by
is
KT.
nothing but phi n. So can I write from here, if I take log on both the side, can I write Kt by Q? So this will be Q phi p. So that is why I have written Kt by Q, and ln will be Na by Ni. Sorry. And phi n, similarly I can write Kt by Q ln Nd by Ni. Any doubts?
No.
Yeah. So we have just established that this VBI is nothing but phi p plus phi n. So if we try to calculate the built-in potential now, so it will be Kt by Q. So what is ln A plus ln B?
Gain to P. Lani into P.
Yeah, so it is AB. So I can write Na Nd by Ni square. So this is the theoretical value or of the built-in potential that is coming, or the barrier that is coming in between the P and N junction. Make sense? Any doubts here, anyone?
No.
Okay, so if not, so let me give you a very quick question. I mean, this is a very basic. So let's say we have a abrupt PN junction. Again at zero bias, let's say the value of Na is 3 10 raised by 16 per centimeter cube, and d is, let's say, which be 10 2 into 10 raised by 15 per centimeter cube, and Ni you can take, I mean, it is, you should remember this value of Ni. It is not given in every question. I'm still talking about, let's say, temperature, which is 300 Kelvin only. So this, I mean, if you remember in the last lectures also, I told you that this value is nothing but 26 milli electron volt at room temperature, or I can write at T is equals to 300 Kelvin. Just for the simplicity of the numerical, I have given you the value also. So what was I going to ask? Yeah, just let me know what is this BBI. Is it doable? I mean, shall I wait for 1-2 minutes?
Yep.
Okay. If you want options also, I mean, I can give. What should I write? I know the answer. So let's say this is 0.7, 0.68, 0.81, 1.04, something like that. Yeah.
Option B.
Okay. Yeah, I know it is answer. So is option B only. So VBI is 0.026 times ln. So this will be 6 10 is per 31 by 2.25 times 1020. So if we'll solve it, it will come out to be 0.68 electron volts or 68 volts only. I hope there is no doubt till now. So shall we move? Shall we move ahead? Okay, taking it as a yes.
Yes.
Okay. So now what we'll be doing is we'll be calculation of the main thing, that is the electric field. That is what we were interested in majorly using the band diagram. The slope of that thing is electric field, right? So how do we do it? As I already told, so it is solved using Poisson equation. So the electric field will change with respect to the position. So let's say, oh, I did not tell, I guess. So this is the charge density. I mean, I assume that you all know what is Poisson equation. So this is in per centimeter cube. And yeah, this is epsilon. This is the permittivity of any semiconductor. So let's say epsilon s I am writing. So what we are doing is we are still doing it for the PN junction only. So let me make a band diagram. Okay. So let's say what we are interested is in the junction, right? So let's say this is 0. Sorry. Let's say this is 0. This is xn. So this is the width, the depletion width on the n side, and this is, let's say, xp, which is a depletion width on the p side. So I'm writing here as minus xp because I've taken 0. So what we just saw is there is some concentration gradient, right? So if I try to plot this charge density, right? Charge density is nothing but the charge multiplied by the concentration. So what do we have on the inside? Which ions? Hello.
P plus.
Yeah.
P positive ions.
And on the p side we have acceptor ions. So this is some positive charge. So q times Na is nothing but the charge density, and as I said, it is constant in the x direction. So this is what I can write, a big plus. So what I'm plotting here is rho v, the charge density. Similarly, so what we have, Na is negative, right? So minus qna is on the n side. So you again see there is a gradient, right? So this is xn, this is xp, minus xp, or let's say. So what we need to calculate is electric field. So please be interactive here. I'll be calculating and you will also try to calculate side by side. So can I write here the electric field is nothing but the integration of rho v by epsilon s dx, right?
Yes.
Yeah. So let's say now that first of all we're starting with at x, which is less than 0, and till minus xp. So I'm talking about this region. What is the value of rho v here? Anyone? You're not able.
Q&A to explain.
Yes. So minus q, and I hope you are able to understand this, right? Any doubts, anyone?
Yeah.
Okay.
No. Yes.
Epsilon S.
Understood.
Yeah. So if I try to integrate it, so n is constant, q is constant, epsilon s is constant. So what I can write is minus q na by epsilon s into x plus some constant c, right? Any doubts? Okay, I'm hoping not. So again, what we establish is there is an electric field present in the junction, right? From here to here, we know that there is certain electric field, and from here to here, there is zero electric field. So what we to calculate this constant, so let's say I'm writing it at C1. So what we write at x is equals to minus xp, the electric field is zero. So I can calculate C1 from this. So C1 will come out to be, so it will come out to be q na xp by epsilon s, minus also will come. Any doubts here? The in the calculation of C1? Take your time.
No.
Yeah. If not, so the electric field on the p side will be. So I'm putting the C1 back here. So it will be q na by epsilon s. I can take common, or in fact minus also I can take common. So what we are left with is x plus xp. So let's say this is equation 1. Any doubts?
No, no,
So if
you can go.
not,
No.
yeah. So if not, you can quickly let me know. Let's say from 0, x is between 0 to x, and what will be the electric field? Quickly let me know. I mean, this will be same, but yeah, what will be the
Q N A.
Na?
Q. N
ND.
D.
Yeah.
Minus divided by epsilon s
Hmm.
x plus xn.
Okay, try to do it. I mean, try to follow the steps. There will be some plus minus difference. So let me know quickly. I mean, try to do it in your notebook or whatever you are having in front of you, and let me know. So Q and D by epsilon is fine, but yeah, there will be some changes. Anything? Come on, this should not take this much time. Am I audible? I hope.
Yes.
Yeah, yeah, okay. Okay. So let me try to change the color here only. So it is Q and D for by epsilon is x plus V2. And again for x equals to xn, we will have e is equals to 0. So from this C2 will come out to be minus Q
X
and D.
minus X.
Sorry?
It should be, yeah, X minus XN.
Yes. Everybody is getting the same?
Yes.
Okay, so that's great. So if I try to now plot it, so this is the x-axis, this is xn, this is xp. So what we have established is the electric field is 0 beyond minus xp. So let me make a thicker line, and beyond xn, right? So This is nothing but a linear relation with x, right? So if you plot it, I mean, if you try to do it, it will come out to be an intercept on the minus y axis, and for this it will come out to be like this. So this is electric field versus position. Is there any doubt how I have made this plot? If yes, please let me know.
Can you explain again?
Okay. So you see, we have this equation for this region which is 0 to minus xp, right? So at minus xp, if you keep x as minus xp, so electric field is 0, right? Because minus xp plus xp will be 0, right? I mean, we already established the boundary condition, and then this electric field. So consider, I mean, let me give you a very basic example. So consider this as y is equals to mx plus c. So this m is the slope, x is like a linear relation. So if you try to plot y is equals to mx plus c, it is nothing but a line, something like this, in which the m will be the slope of this line and this c will be the intercept, something like this. So again here x plus xp, so this term is mx, and this multiplication with q n xp by epsilon s will be c. Understood?
Yeah.
Yeah. So similarly, this line will also come like that only. I mean, this equation, just a linear plot. So y is equals to mx plus c, some intercept. So this is this. So you see the electric field will come out to be maximum at the origin, or the at x equals to 0. So this is what we call as maximum electric field also, and it will be equal. Okay, I'll tell that later. So what I was saying is, I mean, is it clear, the electric field plot?
Yes.
Okay, let me try to explain in a very basic term now. So what we started with this dE by dx is rho v by epsilon r. So this is nothing but a constant, right? If I talk about a certain region, let's say n region, right? Please open your mic. All, yeah.
Yeah, yeah.
So if I try to integrate a constant, what will be the nature of the constant? It will become,
Well, you're integrating the constant. I mean, it
uh,
will have an like the x term here.
yeah. So it will become linear, right?
Yeah, it will become linear.
So this is what you see. So the
Yeah,
potential.
that part we understand. Like we have to
Oh,
replace the x term, and then we'll get the value of the electric field.
yes, yes. So similarly, if I try to integrate it once more, let's say, because what we know is E is minus dV by dx, right? So V is integration of minus E dx. So what will this linear thing will become?
Yeah, can you repeat?
So what I was saying is, once we integrate the constant, we get the electric field, right? Now electric field is minus dV by dx. So V is
I
the,
mean, the potential.
yeah. So potential, yes. So potential is now the integration of electric field, and electric field is linear. So what will be the relation between the potential and the position? I mean x. It will be,
Integration.
yeah, integration of linear is
RAM function.
not ramp. It will be x square, right? Parabolic.
Oh yeah, yeah, okay, okay, yeah, yeah.
Yeah. So you'll see that the final potential plot will be parabolic. So this is what is this. This is parabolic. This is what we are aiming to solve. Understood?
Yeah.
Yeah. I mean, I was trying to give you a bigger picture. So we have got to know that the maximum electric field is at the what to say, at the origin. So what I can write, at x equals to 0, this Ex is E max. So I can just replace E with E max and put x equals to 0. So QNA, it was x plus xp, so I am writing 0 plus xp by epsilon s. It will be also equals to the n side, because we need to have a continuity here. So if you need to have continuity, it will be q and d. It was x minus xn by epsilon s. Can I write these two equations?
I have one question.
Yes.
You said that from the equation we got to know that the electric field is maximum at the center point. But what is the intuition between? I'm like behind that. From the mathematically we did derive that it is Emax, but
Hmm.
and what is actually happening there?
Yeah.
Is it
So
because maybe the concentration is same and that's why?
so the maximum change
Yeah.
in the concentration is at the junction, right? At the middle part. So that is why there is maximum will change. So whatever the maximum change will be in the concentration, wherever will be the change, it will be the maximum at that point, the electric field. I mean, physics wise, I'm trying to tell, not mathematically. So,
Okay.
yeah, so wherever there is this abrupt junction, I mean, ideally it was like this, right?
Mm-hmm.
So wherever there is a concentration change abruption, there will be electric field. That is the maximum. I mean, it will slowly go. It will slowly reduce on both the sided, and it will continuous. I mean, it will be ultimately becoming zero at the bulk. Make sense?
Okay. Yeah. Yeah. Thank you.
Yeah. So if you understood this, so what I can write here is minus q na by epsilon s into xp is q nd minus xn by epsilon s. So this everything will go away, and what we are reached to a very important relation. This is naxp is equals to ndxn. This is a very important relation. I mean, this is used to solve many problems. So the acceptor ion concentration multiplied by the length of the p type is equals to the donor ion concentration multiplied by the length of the n type. Any doubts still here? Please let me know if you have any doubts.
Understood. Yeah.
Yeah, okay. So that is
Fine.
it. I mean, I'm not going to a further derivation. So what we have established is electric field is something like minus qna by epsilon s x plus xp, which is 0 to minus xp, sorry, minus xp, and it is q and d by epsilon s x minus xn, which is from 0 to xn. And if you integrate it once, what we'll get is we'll get the potential profile. So I'm writing it directly, so it will be some x square and some constant again. So what we get is, let me try to write the relation only. So for p type, what I'll get is I'll get some x square term. So it will be qna by epsilon s. It will be x plus xp whole square. There will be 1 by 2 also, because the integration of x is x square by 2. And similarly, so I'm not writing, this is for 0 to xp, and similarly I'll get q and d uh, by epsilon s. Okay, so there will be some constant also, I guess, associated with this, or not. If this is the final relation that you will get, so this will be xn x minus x square by 2 plus qna xp square by, yeah, something like this you will get. So this is the potential on the n side, and this is the potential on the p side. So I'm not deriving the potential part because this is again same. You will integrate it again and you'll give the same. So the main intention of telling all this was, we started with this. This is a plot of rho v, which was some q and d on the n side and some minus q and a on the p side. We integrated it once. We got, okay, let me make it again. We integrated it once. We got the electric field profile, which is something like, let me change the color. 0 here, something like this. Yeah, something like this. So this is electric field, and similarly if I change the color once more, for potential, so this point is xn, and oh, change the color. Similarly, the potential will be something like this, parabolic. So I mean, uh, the energy is minus qv. So the band diagram that you will see is, it is going like this, right? So this is a negative of that. So this is vbi only, and this is the potential profile. X. Any doubt on this page?
No, yeah, understood.
Yeah, great then. Okay, so this is what is depletion width, right? So there is a thing called as depletion width, which is nothing but xp plus xn. So we do have a formula for that. Do you want me to derive it or just write the formula? I can do the derivation also. I mean, it is short, but should
No,
I?
you can do it and we'll understand.
I should write directly.
And you can do the derivation.
Okay, 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 fine.
And W is the width of the depletion region, so
Yes,
it's
so it is, yeah,
straightforward, right? XP. So do we also have derivation for this?
yeah, yeah. So I mean, from the equations that we already have, we can
Hmm.
have a formula. So what we have just established, first of all, what we just established was xpna was xnnd. So this is, let's say, equation 1, and also the vbi is, okay. So I guess I forgot to tell you. So vbi is nothing but here, right, at x equals to xn. So I can calculate the potential also. So vbi at x equals to xn is, so if I try to write here qnd by epsilon s, so there is a this formula, right? If I put x equals to xn, then I'll get the vbi. So I'm doing that only. Sorry, I'm doing it here. If you put the value of x equals to xn, so what you'll get is q by 2 epsilon s, sorry, nd xn square plus na xp square. This is what you will get after putting x equals to xn in that formula. And there is one more formula for vbi. So can anyone tell? We just derived it in the initial part of this class. Come on, guys. VBI is,
5
K2
plus
by
5p plus 5n. Oh,
yes, yes, yes. So from that we got to know that this is nothing but na nd by ni square. So now what we have seen is this. So can I write xn as xp na by nd? See, if I do some mistake in between, please be aware and let me know also. So I'm putting this xn here. So what I'll get is VBI is q by 2 epsilon s. So I'm putting this xn, right. So nd will come niche and a square will come above. Okay. Xp square will come and plus na xp square. Okay. So VBI will become q by 2 epsilon s xp square. I can take common. It will be na square by nd plus na. I hope there is no mistake. So what I can write is 2 epsilon s VBI by q. So I've put it here and q has come below. It is nothing but na square plus na nd. I'm taking the LCM by nd xp square. So from this I'll write xp as under root 2 epsilon s by q. VBI is also there, and I can write this as nd upon na square plus na nd. Any doubts still here?
yeah, understood. Well,
Yeah, okay. So
straightforward equation.
xp will be, again I'm writing 2 epsilon s by q VBI. So if you try to solve it, if you take nd by na common from this, it will come out to be 1 plus na nd. I've taken na common in the denominator, so na plus nd is left.
Yeah.
Similarly, if you try to calculate xn, so that will be also the same. The only difference will be VBI, it will be na by nd, and this will remain the same. Any doubts in these two equations?
Yep, yeah, it's clear.
Yeah, so W is nothing but xp plus xn. So if you just add them, the final relation will come out to be 2 epsilon s by q pvi, and it will be 1 plus na upon 1 plus nd. So this is the final formula that you get. This is again very important. I mean, you must have seen it in the lectures also if you have seen them. So in the lectures there are derivations, right?
Hmm.
Okay. So any doubt till here? So what we have established now, we have calculated the depletion width. We have a formula for electric field. We have a formula for potential. We have a formula for maximum electric field. Any doubts?
No, no, we can continue.
Okay. I guess I need to take one more class for this diode also only. Okay. So let's try to do a question now. I mean, try to be quick in responding. So the question is something like, I've taken a abrupt PN junction. So what we have Na as 10 is plus 17. Please sit with your copies and pens and try to let me know the answer as quick as you can. NDs, let's have taken 10, 5 into 10 is per 15 per centimeter cube. Temperature is again 300 Kelvin. Ni you already know. Let me write that also. Yeah, everything is this. So the first question is, I mean, you can do it if you can. You need to sketch the equilibrium energy band diagram. Energy band diagram. So I'm writing energy band diagram as EBD. Second is calculate EF on each side of the junction. Third is determine VBI. Fourth is determine XN and XP. And fifth is determine the Emax. I mean, this is what all we have done today. So this will give you the answer to every question. So are you willing to try it by your own? Try to do the easier part first. Maybe these parts are easy, then you can sketch. Are you trying or should I?
And I'm doing it. VBI is 0.73 built-in one potential.
Okay. 0.73 you are saying.
739. Yeah.
739. I hope everyone is calculating it. I mean, it will require some calculation. So do you have your calculators with you?
Yes.
Sure. Let me know the other answers also. Any progress? Let me do it side by side, otherwise it will take a lot of time.
Well, electrical permittivity is 8 point.
Yeah, yeah. So, I mean, for silicon, it is what was the constant? It was 11.7 times 8.85 times 10 square minus 14 farad per centimeter. So everything is in centimeters, so you need to find. So VBI, I guess, is correct. It is 0.739 only. So maybe, so EF on each side can be calculated by again the same. So EI minus EFP will be 5P, which we already established. It is nothing but KT by Q ln. So P side will be Na by Ni. So sorry. So 5P will be KT by Q ln Na by Ni. And if you do it, it will come out to be 0.408 electron volts. Similarly, so this will be Q phi n, it will be Nd, it will come out to be 0.33 electron volt. And VBI, either you can write phi p plus phi n, or you can also use the direct formula, so it will come out to be 0.739 electron volt. Again the xn, so xn ke liye we have that formula, the bigger one. VBI is Nd by Na, 1 plus Na plus Nd. This is the formula. Xn is Na by Nd. Sorry. This is Na by Nd. You keep all these things. Are you trying? Anyone with any answer? So please always keep your calculators for this course. So this is 0.738 or 9, whatever it is. Na by Nd is 10 to 17, 5 into 10 to 15. And then this is 1 upon 5 to 10 to 15 plus 10 to 17. So this is 5, this is 2, this 15, okay, 15, 13 minus 13, so minus 13, what I can write is minus 5 from minus 10, and this is 2 into 11.7, 8.8, 5.738, and in the denominator it is 1.6, 1.05 because of that, and 5.
That's 4.25 into 10 power minus 5.
Okay, so this bracket should come to 4 point something. Yeah, the order is correct. I mean, so I'm writing it, let's say 4.2 something is coming, 10 to the minus 5. So this is in centimeter. So what you can write is this is 0.425 micrometer. Similarly, you can calculate the XP also. I mean, the formulas
We
are,
can use that. I mean, if okay, the condition is not given, is it? The equilibrium.
yeah, it is all. I mean, this question is for equilibrium. I've written it.
Okay, okay. We can use that other formula.
Yes. So XP will come out to be 0.02132 micrometer. So now what you see here is what we establish is NaXP is NdXn. So you see in this question, this Nd is higher. No, what is higher? Nd is lower. Okay. And Na is higher. And these two should be equal. So XP will be higher or Xn?
I mean, whole concentration is more. So I mean, the depletion region will grow more towards I mean, the inside.
Yeah, yeah. Again, the question is XP will be higher or Xn?
Yeah, I mean, Xn will be higher.
Yeah. So to make them equal, this will be higher and this will be lower.
Yeah,
So
yeah.
again, you see is that the depletion region, if I say this is Pn, So Xp is lower, so the majorly the depletion region will be in this side, the N side. So you need to be aware that wherever there is higher doping, lesser will be the depletion region on that side. So that is why for the metals we don't have any depletion region. So let's say this is a metal and this is a semiconductor. So there is no depletion region in the metals because they are very highly concentration. Make sense?
Yeah. I mean, we also use this concept in I mean, to reverse bias this PN diode. When when we form a FET, right?
Yeah.
So
When we
from
form what?
subs
When we form
FET,
what?
FET. Transistor,
Okay,
transistor.
MOSFET you are saying.
MOSFET, MOSFET. So
Okay.
we have the high. We also do the halo implants.
Hmm.
Increase the doping for the substrate. So when we increase the reverse bias, so the depletion region grows into the not inside the substrate but outside.
Yeah, yeah.
Within
Okay.
the so yeah,
Yeah, I'll try. I'll explain
it
that.
will reach to a leakage path. Yeah,
Yes, yes, yes. I'll be explaining that thing in week 6, so don't worry.
okay, okay,
Yeah,
okay.
yeah. So MOSFET
Right,
is a
you mentioned
complete
that.
topic.
Thank you.
So yeah, I mean the basic giveaway here is that wherever there is higher concentration, the depletion region will be lower in that particular site. Everyone, is it clear? And yeah, W you can write XP plus XN. So these two sum out, so it will come out to be 0.44 something micrometer. And Emax you can again calculate using that formula Q N D XN by epsilon I or Q N XP by epsilon I. So it will come out to be, you can do it in, I mean at your homes, it will come out to be this. Okay, so now come a very good question. So let's say now what I have is, so please follow the concepts, not just blindly write anything. So now what we have is, let's say I have a N plus N silicon device. So you already know now how to make a band diagram. So N plus N silicon device, I have ND1 because both are N. So ND1 are, let's say, 10 is per 18 per centimeter cube. ND2 is 10 is per 15 per centimeter cube. Again, Ni you know, let's say for simplicity, let's take 10 is per 10 per centimeter cube, and temperature let's take 300 Kelvin. So you need to calculate VBI here. So this will like very well judge your understanding. So don't just blindly go towards the formula. Try to make the band diagram and then see what is happening. You'll get to see a very interesting side of it. So first of all, try to make a band diagram of this and then try to calculate the VBI using that thing that we did, phi p plus phi n, something like that. Make sense? Any doubt?
No, I understood. Here, the electrons will flow from N plus to the N region.
Hmm.
So, when we calculate VBA also, we only consider this, ND1 and ND2.
Yes, yes,
Yeah.
yes.
So, here, yeah, that's what.
Yeah, just try to calculate the VBI. I mean, just try to go towards the building of the formula that we did. So it was NaND by Ni square for PN junction. Similarly, I want something for N plus N junction. So what will be that? That is what I want to know. You can take 2-3 minutes.
26 millivolts into ln of ND1 into ND2 divided by Ni square.
So that is why I said don't go blindly towards that. Try to
Okay.
calculate it. Yeah.
Okay, okay, okay.
Yeah. So whosoever, if you come up with the formula, anyone, you can open your mic and let me know what have you come up with. Make the band diagram, that will be easier for you. Anyone come up with anything? Anyone made the band diagram of this? Hello, am I audible?
You are audible.
Okay, okay, yeah. So, okay, so no progress. So let me try it. No problem. So again, it is at thermal equilibrium. So this.
Just, I'll tell my understanding.
Hmm.
So, I mean, for the ND1, uh, it is in a higher concentration. So, for the ND2, right, we'll calculate the acceptor, right? I mean, applying the
Okay.
formula of Ni square and then
Acceptor. No, no, no. There is no
not
p-type material in this. So do no acceptor. Let me give you
a
like
whole
so.
concentration.
So no whole concentration. Why would you calculate a whole concentration if both the materials are n-type? So I
Okay.
mean, okay. So let me give you a very basic understanding. So this is all about today only. So what I said is the Fermi level will align, right? So the flow of electron is from higher Fermi to lower Fermi. So let's say this is here. This is EC. This is, let's say, EF1 and EF2 are aligned now. This is EV1 and this is EI. So this is what we know is phi 1, right? Or Q phi 1, let's say. And the second thing, because the flow is like this, so this will go down. So something like this. And this EI will be also same. Oops, sorry. So this is EI2, this is EI1, this is EV2, this is EC2, and for this will be Q phi 2, and the Q VBI we know is this. Has anyone made this band diagram? If you have made this, then only you will be able to solve this problem. Otherwise, you can't. Anyone who has made this thing or understood how I made it? Okay, am I audible
Well,
or is
okay.
it
I
getting
understand. Yeah,
tougher?
yeah, audible.
Is it tough to understand or what is the thing? I want I want everyone to be interactive in this because if you are able to understand this, then it is good. Otherwise, I can explain better.
But I understood the left side part, right side.
What is I mean after the bending, you are not able to understand the
Okay, okay,
right
okay.
side. You are saying so.
Right.
See, the flow will be from higher Fermi to lower Fermi. So whatever will be at the higher side will go down, right? I mean, okay. Let me give you an analogy from there. I guess that was very easy to understand.
That I understood when it will go lower because it is high concentration.
Hmm. So it has gone lower. So yeah, this is it. I mean, so what part did you not understand?
Okay.
The Fermi will always be above the EI because both are n. So this is n plus, this is n.
Mhm. Okay, okay.
So anyone else having any doubts in this band diagram, please let me know here only. Otherwise, there is no point of having these live sessions. Please, everyone, try to be interactive. I don't want to take names. Please try to be interactive, people. Okay, so fine. So if this is QVBI, so this change is also QVBI. So here what you see is QVBI is nothing but Q51 minus Q52. Make sense? Anyone? Are you able to understand this? If not, you can say no. There is no issue in that. No?
Well, I understood when I'll have to go through again.
Sure,
So
sure,
that
no
I can
problem. So,
better understand. Yeah.
yeah, sure, sure, no problem in that. So, this VBI is phi 1 minus phi 2. So, here comes the main thing. So, this will be ln nd1 by ni minus kt by q. No, sir, need more clarification. Okay. So, which part you did not receive? You can open your mic and let me know. Samaya. Yes. So, I mean, the band bending is not clear. Hello.
Yes, sir.
Yes, yes. So, the banding is not clear, you are saying?
Yes, sir. That banding is not clear for me.
Okay. So, do you agree that this part will go below and this part will be on the higher side?
Sir, pardon?
Do you agree that this part will be on the lower side because of the higher concentration and this part will be on the higher side? I mean, do you agree till here?
Yes, sir. Yes, sir. That I understood.
Okay. So I mean, then there is no issue there, I guess. So, this part is n plus. Oh, sorry. So, you see, so if I not bend the diagrams, so this part is n and this part is n plus, right? I mean, I hope these two are very clear that the Fermi level will be closer in n plus and it will be far away from EC in n, right?
Yeah, okay, sir.
Yeah, so that is why. So this has gone a little bit below. So you see the Fermi level needs to be aligned. So to get it more closer towards the EC, so this EC will go a bit down and this will remain down. So that is why we have this EC for the n plus closer and the EC for the EF for the n part far away from EF. The bending makes sense now?
Yes, sir.
Okay, and whatever will be the change in EC will be the change in EI because these two are parallel, the EC and EI, right?
Okay, sir.
Yeah.
Understood.
Yeah, and then the EI minus EF. So this is Q51 and this is Q52. So if I make larger line, so this minus this is coming out to be QVBI. I mean, you can go through it once again, and I'll maybe in the next lecture I'll start with this problem only. That is, I guess, will be better. Now what I can write, the phi 2 is Ni. Yeah. So due to this minus, the final VBI will come out to be KT by Q ln ND1 by ND2. It is not even dependent upon Ni. So this was the main thing that you have to capture. Any doubts, anyone?
I mean, I understood, Anant. I mean, the only problem I faced is so replicated that, right? QB1. I mean, the change in a EC will
Hmm.
be parallel to even for the valence band and even the intrinsic.
Yes, yes. So
So that
these.
I didn't see it before.
Okay. So
Okay,
that
that's
is
clear.
what I did in the PN part also. If you wait. So this is what I did in the PN part also. The difference between EIP and EIN, I make the VBI only.
Uh,
That is the
yeah,
difference. So this barrier, I mean the barrier that shows at the
yeah,
conduction or the valence band is what is built-in potential. Fine.
yeah,
Yeah. So no problem. I'll start with the same problem in the next week also. That is fine. So now this has become quite easy, I guess. So this is 0.026 ln. The higher was 18 and the lower was, I guess, 15, something like that. So the VBI for this will come out to be, you can try it home, 0.1726. You can, I mean, yeah, you can see this particular case again, and maybe we can start the next lecture with a problem of P plus, something like that. That will give you more understanding. So please do go through this particular problem. That will help. Is it fine?
yeah, yeah. Thank you.
Okay. Yeah, okay then. So since I have not covered any diode equation also, so I'll be covering that in the like continuously for week 4 and 5. I said that there will be some topics that can get mixed up. So that is fine. So we can start with a similar problem. First of all, a PP minus or a PP plus problem. And then we can go towards the biasing of diode and all the diode equations and some numericals for that.
Yeah,
So I hope it helped. So yeah, that is it. Maybe we can, yeah, we can wrap up today's session and we'll meet next week same time.
yeah. Thanks, Anant.
Yeah, yeah,
Thank you.
yeah. Thank you everyone.